right, what's that thing I just drew?
A pick.
Yeah, a pick. A pick for what? Pickaxe. What do you use them for?
Mining.
Yeah, you use them for mining. So let's erase this and just write the word mining. Before we get into data mining, let's just talk about mining. What the hell is mining?
It's like you're extracting like random artifacts and then like you're like giving it to another person.
Yeah, so usually, what sorts of things are typically mined? And I'm not talking about information or data, I mean literally mining.
Gems.
Gems, gold, what else? Oil, bitcoins, and it's the same sort of thing. And when you're mining, where are you? Describe your physical location when you're mining. In a mine, where's a mine?
Underground.
Underground, a hole in the ground. So what do you spend most of your time hitting with a pick? Rocks or what else is down there?
Treasure chests.
Dirt. Dirt and rocks. Most dirt and rocks are useful or useless to humans.
Useless.
Yeah, they're generally pretty useless. So most of the time you spend a lot of time digging around in dirt and rocks, wasting your time, except mixed in amongst the useless stuff is a lot of really valuable things like gold and diamonds and gems and oil and coal and things which can make you a lot of money. So the whole point of mining is you go underground, you hang out in some dirt, and then you find some valuable things hidden amongst the useless stuff. So, same idea with data mining. What is data mining? You go amongst data and you try to find the valuable nuggets that are hidden there just in the same way that gold is hidden in dirt, or diamonds are hidden in rocks, or coal is hidden underground in whatever coal lives in. So, when you're data mining, you are, instead of in dirt, you're just in a data set. So, what do we have right there? A data set. This is just a set of data. This is something which a computer could look at and process. It's just a bunch of numbers, except for the one on the right where I use these to show that the first one has 2 in the same column. So, anyone have any guesses on what this is a data set of, by the way? Like what each column responds to? Any guesses? I'll just give you a minute while I then erase the word mining and give you all a final clue, which is to add a final see if this helps.
Oh, IP address.
Nope.
Oh, that's definitely not IP address because there are no.
Coordinates?
So, well, I'll tell you, with each individual, so each column with the comma is a totally different line. So like this number is separate from this number is separate, so it's not one big number. So I heard the correct first one. This is zip codes. These are all 5 are zip codes, as in the thing at the end of an address. Does anyone know where all these zip codes are?
Manhattan.
Yeah, Manhattan. These are 5 Manhattan zip codes, which are all in New York State. So that's what the last one is. All New York State, all zip codes. What are these ones? Anyone have any guesses?
I am guessing it's like the house location, like no.
Not quite.
Residence?
Say that again?
Residence?
Yeah, this is
Oh,
the
yeah,
population
residence.
in that zip code. So in 10001, you have 23,947 people living there. Does anyone know what this number is? Income. That's median income. So if you were to take everyone in there and pick the person who's exactly in the middle, this is how much money they're making a year. Anyone know what this one is?
Age.
Pardon?
Age. The age of the population.
Average.
Nope.
Any percent?
I'll give you a clue of what the unit is.
Square meters of apartments?
Square miles. It's the size of the district. So, and then anyone know what this fourth or this fifth one is? This one is 10 and 12, this is 7, this is 12, this is 10, this is 10. Congressional district. So this is New York State 10th District, so their representative is somebody in the United States House of Representatives, which is shared with this one. Part of District 1001 is in District 12 and parts in District 10. 10002 is in District 7, and this is District 12. So it's who your House of Representative is. So it's who you're voting for when you get to the ballot, whether you're going to be voting for the people who represent this area or that area. So this is just a common data set. Now look at this data set. You now know what it is. But even before you knew what it is, the same thing would have applied. Look at this and tell me something useful, some patterns that exist in this data. Can you look at it and tell me what some of the patterns are? Specifically, which ones are related to which other ones?
Maybe the population size and the income.
Yeah, so which way are they related?
It seems that the smaller your population is, the larger the amount of income.
Yeah, it looks like the more wealthy areas, so these two, have much smaller populations. And the largest population is the one with the smallest income. What are some other things which you might be able to find out just by looking at this?
That the last two live in the same exact district.
Yeah, so you know that these two, because districts are somewhat geographical, you know that these two are very close to each other in some sense. They probably touch, or at the very least are related to each other in space. And which other one is probably relatively close by or touching?
First and the third one.
Yeah, the first one, and then you also know that the first one and the third one probably touch. And then this one is the odd one out, which is connected with something else. Yeah. What else can you tell me about it? What else is correlated here?
They're all from New York.
Pardon?
They're all from New York.
Yeah, these are all New York addresses, so that's something interesting. Here's another thing you can probably learn, is that what the zip code is very strongly related to the state it's in. You don't have New York City ones like, these are nicely ordered, so that at least there's some system in it. You're able to look at the data set and do this, but you first had to guess, when you decided like to look at how these two are related, the smaller this one is, the bigger this one is, it's easier to make those calculations if you know what on earth you're talking about. Or another one, look at this column. Just look at this number. Which other ones is it related to?
None.
There are certain patterns you could find. Find the smallest number up here. Which row has the smallest number?
Oh.
This one. This is 0.07, which is significantly smaller than all of the others. It's also relatively high in the income chart and relatively small in the population compared to the others. Now, how much this matters, you'd have to do a little more research. But just looking at these numbers, it can be hard to tell what is related to what. And this is just 5 rows and 6 columns. And you all knew what each one correlated to. Who could do this a heck of a lot faster and a lot more quickly than you can?
Computer.
A computer. A computer could look at this data set and not only tell you for something this big, but something hundreds to thousands of times bigger, and give you a literal number of how much things correlate with each other. So you might be able to see at this and see like it's a 0.07 is related to this, so it's kind of got something to do with this one being related to that, but then this one is much bigger but also has way fewer people living here. So like what's going on there? Does anyone actually know why that's the case? Why, I looked at a map today, why this is quite large but it has a tiny population? It basically, this area code just covers Governor's Island and Battery City Park, or Battery Park at the bottom. So there's basically no houses in this area, most of it is a park. So there's not actually that many people living here. So that's what we're talking about with data mining, is what you just did, only a computer can do it without knowing what any of this means, and can do it over huge, it's just number crunching. If you plug this in as is, a computer doesn't need to know what each column is. It can just tell you, this number is related to this number. When this one goes up, this one goes down. And it'll give you a percentage likelihood that if you did this, like if you tell it approximately, if I have a population of 25,000 and I'm in New York City, how much money should I be able to expect them to have? And that's what a computer can spit out in a matter of, seconds. It's just an R number for anyone who's taken a statistics class. It's just a correlation number. What do we mean by correlation, by the way? What is a correlation between two numbers? Or two sets of numbers?
A relationship?
Yeah, it's just a relationship. It's basically the idea is, if you know one number, you can make predictions about another number. That's all a correlation is. So, what are two numbers or two things in the world which are correlated? We don't have to worry about this sort of thing, but like what sorts of things that you encounter every day are correlated and you know they're correlated?
Like weather?
Yeah, so weather and what?
The Uber fare prices and
Say that again?
the Lyft and the Uber when the weather goes up.
Yeah,
Sorry.
Lyft and Uber prices are related to weather. Specifically, when it gets colder and when it gets rainier, the prices go up. So that's one correlation. Here's another one. Or no, let's think of some more. There's a ton out there. You encounter them every day.
Well, I think when you go into anywhere regularly and you buy stuff and it becomes popular. then-
Yeah, so here's things. How many people are buying a product and how popular it is? By which I mean like how much people are talking about it, or how much it shows up in songs. Like the number of times that somebody is talking about Gucci in a song and the amount of products that are sold by Gucci. Those run together. What are some more?
The date and the flight prices, so if it's closer to a holiday, flight prices will go up.
That's another really good one. Yeah, if you try to buy a flight around Christmas time, it's way more expensive than if you're trying to fly in like the middle of February. And that's another good correlation. Here's another one. Let's see. Just go with some basic ones. Tell me some things that are correlated with height.
Or the apartments.
Oh,
The apartment?
oh, I
In
think
the
I
New York
know.
City.
I was thinking human height.
Oh,
Yeah.
sorry.
Yeah, human height.
I know what you mean. Sports?
So one thing, and so these are somewhat messier, is one thing is that there are certain sports which are more correlated, and it goes other ways. But here's another pretty obvious one, weight. The taller you are, on average, the more you weigh, because you have more body mass. Here's another one that's correlated, height and
Age.
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 Like babies are small, adults are big. That's another strong correlation. So these are the sorts of things we're talking about, and you don't need to know, and the great thing about a correlation is it doesn't explain why they're related. And this is something you've probably heard before, correlation does not equal causation. So just because you know two things are correlated doesn't necessarily mean that one causes the other. So for instance, there are some very strange correlations out there, and people like to think like, oh, that's proof of this, but really, either they're both caused by something else, or et cetera. So, for instance, you can look at these and find some interesting correlations and identify probably what the causes are. So, why is it that the more this one goes up, the more this one goes down? What's the reason there? Why is it that the higher this number is, the lower that number is?
It could be because of the square miles.
Yeah, so here's the fact as well. There's also a size element. So these are all relatively similar. We're all under a square mile. Now this one is teensy tiny, so let's just throw that one out. But if we're looking at like this one, 0.62 and 0.88, there's a big difference, but it's not like, there's a difference, but it's not crazy. It's not like this is like the size of Wyoming or Alaska, and this is the size of New York City. So what we have here is in a relatively similar sized space, you have a lot more people living. Now if there's a lot more people living somewhere, what's probably true about their houses? Compared to, so look at this person here. Yeah, let's just go with this one. This is a big gap in wage. This is $81,000 a year versus $33,000 a year. That's a huge amount. It's more than double that. There's also less than half as many people here in what's relatively the same size. Why is it that this number is so much higher than this one? Well, if you have this many people smushed into this much area, how much area is there per person?
Less.
Less. Specifically, what determines how much area you get per person? Rent. Your apartment size. And what costs more, a little apartment or a big apartment? A big apartment, because in New York City, space is limited. So why is it that this population is higher and this number's lower? Well, this population is lower and this number's much higher. Well, if you're making this much money, you can afford a bigger apartment. And if you afford a bigger apartment, you're taking up more space within the neighborhood, so there's less apartments to be there, which means there's going to be fewer neighbors that you're competing with. Compare that to this, in which the reason why this number is so high, there's this neighborhood down here is like a very southeastern tip of Manhattan. So if this is Lower Manhattan, it's like there's a little lump here, and then so it's like right here. Does anyone know what's there?
Chinatown?
Lower
No.
East Side.
No.
Oh, the east side.
Specifically, there's a bunch of projects there. So there's a lot of large numbers of people living in a relatively confined area, and also older buildings where people generally who are living there have a lower average income. So that's what you see with these sorts of correlations. Is just because there's a correlation doesn't mean, it's not like because there are fewer people here, suddenly there's more money. It's rather that they're both tied in with how big your apartment is, etc.
And I think you also pointed out another one, like the location, because the zip code could be also an indication of what the variance is between.
Absolutely, and what you find is where these zip codes are is also very much, because certain places in the city are prettier, newer, nicer than others. So if you look at this, you can find out where in the city we're talking, which is also going to explain why people want to live here. So like this one here, it's a tiny amount of space, but more importantly, if you're living there, you have a giant waterfront view in a brand new building. To live there, you've got to have a lot of money. And so these are the sorts of things which we with our minds can do, but even without having to know all of this, a computer can just look, and what it can do is say, okay, if we know where somebody lives, we can predict how much money they have. Or, more simply, if we know one, we know number three. And if I tell you now, if I were to tell you that this person lives in 1003, and I were to tell you, guess how much money they make, how much would you guess? Yeah, you'd guess 90,000. You wouldn't guess this one because that's not their area. So this is the way in which just correlations can be used to make predictions. So the basic idea behind data mining is simple. You get a bunch of data stored in a computer. You just put it into something as simple as an Excel sheet or something equivalent to an Excel sheet which can be processed. Step two, you just run a computer program that's designed just to notice patterns in the data. So in the same way that you look over this and just go, oh, when this one goes up, that one goes down. You just have a computer program do that at the speed of light. That's how fast computers work, and they're much better at crunching numbers than we are. Then, once you have that, you identify, so the computer might not know which numbers go together, but as soon as you see which columns are related to each other, you can know what's related to what. So, if a computer spits this out and tells you 2 and 3 are related, you then go back to your data set and say, oh, population is inversely correlated to wealth. Then what can you do with this information? When you've got relations between pieces of data, what can you now do which you couldn't do before? So you've got this huge data set, and you now know that somebody is who lives in a certain area code is likely to make this much money. Now, what can you do if, say, you're an advertiser? What information do you have now, Christina?
So you can just, like, for example, Gucci advertisements versus, like, I don't know.
Yeah. So here's something. Say this is not, you do not publicly know how much any individual person makes if you're a company. So say you're Gucci, and you want to sell your very, very expensive shoes to people. You know that you need to advertise to people who are going to buy your shoes. I, for one, have never and will never have enough money to afford Gucci shoes. I'm not somebody worth advertising Gucci to. However, they're not going to know that just by, like, I don't walk around with a price tag on my head. How might they be able to identify how much I make as an individual? What are some good ways of guessing?
By the area code?
Yeah, so one thing you can do is just look in public records and see where I live. Or you might see that somebody moves into a neighborhood, or you get a mailing list and you know where they live. You can now, just on the basis of this, know about how much money they're going to be making, and therefore whether they're going to be a good customer for you as Gucci, and whether it's worth your time to send an advertisement to this person who's now moving into this area code.
And also maybe like put physical advertisements in places where people are more likely to buy certain products.
Exactly. A big billboard for Gucci is worthless if you put it in the middle of like a Nebraska farm field. Like the pigs and the corn plants are not gonna buy Gucci. If you put them on the Upper West Side, or you put them in Lower Manhattan, you put them in Soho, now we're talking. Now you can make some money, you can have some influence. So exactly, these are the sorts of things that you can use this information on. So yeah, it's just a matter of you can look, and here's the great thing about data mining. Once you have a large enough data set, you don't need to have complete information about someone to make relatively informed judgments about what they are interested in and what they do. So for instance, if I now know that somebody's moving here, I can make predictions about all the other ones. If I'm say I'm running for Congress in New York State District 10, and I need to convince people to vote for me, where am I spending my time?
1004 and 1005.
Yeah, and specifically, if I'm looking to find people to help me with fundraising, where am I going to campaign? So 1001, 1004, and 1005 are all areas that I represent. And specifically though, if I'm a candidate, who do I want to spend my time talking to looking for fundraising?
04,
Why 04?
because they have the most money.
They have the most,
But not only the most money in variation to the amount of people.
Yeah, exactly. So if I can get through to these people, there's not many of them, but if I can get through, they have a lot of money. And here's just a fact, people with a lot more money can donate a lot more money to a campaign. There's a reason why these